8.1/8.2 Systems of Linear Equations. So this is a topic that you probably remember from Math 95 a little bit vaguely. We're going to talk more about it here. So a system of equations is going to be a system consisting of two or more equations involving two or more variables. So for instance, these two systems right here each have two equations and two variables, x and y. This system right here has three equations and three variables, x, y, and z. And the goal of a system of equations is to be able to solve them to figure out what values of x, y, and z, in some cases, make both of these equations true statements. Which values can I plug in for x and y such that when I plug it in here, I get 9, and when I plug it in here, I get 18. So, brief overview of systems of linear equations. Let's talk a little bit about the solutions of systems of linear equations. So a solution to a system is going to be an ordered pair, so that's just a coordinate point x comma y, or in the case of three variables, it's an ordered triple, so you have x, y, and z, and it needs to satisfy each equation in the system, meaning when you plug them in, just like I had said before, you get a true statement. Graphically, if we're wondering what it looks like, you have two lines. So imagining both of these guys, these can both be solved as y equals mx plus b equations, which we could then graph in the plane. So if I could graph both lines, the solution is going to be that place where they intersect. So graphically, the solution is the place where they intersect. But when we talk about the solution, we're not always talking about it in the plane. We're not always talking about the graphs. And the solution then is just the ordered pair x comma y, or the coordinate point x comma y. So let's look at determining if an ordered pair is a solution to a system. So we're given a system, and then we have two different points we're going to try out. First, we're going to try out 3, 3. So that's plugging in 3 for x and 3 for y into both of these equations. So for the first equation, x plus y equals 6, plugging in, it's x plus y equals 6. So plugging in 3 for x and 3 for y, 3 plus 3 equals 6, 6 is equal to 6. So that equation works. Let's try it with the 2x minus 5y equation. So 2x minus 5y equals -2. Because it has to work in both of them. So plugging in 3 for x and 3 for y, we get 6 minus 15 is equal to -2. This is going to give us -9 equals -2, which is going to be a no-go for us. So because it worked in this one, but it didn't work in this one, 3, 3 is not a solution to the system. They have to work for both equations. Now let's try 4, 2. Once again, plugging them into both equations. So x plus y equals 6. 4 plus 2 equals 6. 4 plus 2 is equal to 6. So it works in the first one. For the second equation, 2x minus 5y equals -2. Plugging in 4 for x and 2 for y. So 2 times 4 is 8, minus 5 times 2 is 10. And 8 minus 10 is indeed -2. So because it worked in both equations, we got true statements in both equations, we can say that this is a solution to the system. So we can take this idea of plugging in a point to a system and expand it to 3 dimensions. So we're now going to be determining if an ordered triple is a solution to a system. So we have 2 different ordered triples, and we want to know if it satisfies the system here. So this is going to be x, y, and z in both cases. Now, it might help with this one to work our way backwards because it's most important that z is equal to 5. So if we just go down here and look, z is 5 in both cases, so we can kind of check that one off. But that would be an easy way for us to tell if one of these wasn't an ordered triple, wasn't a solution to the system, would be if one of these had like 1 for the z value, because it says right here z has to be 5. Let's do the 4x minus 3y plus 5z equals -7 part. So here we have x is 8, y is -2, z is 5. So 4 times 8 is 32. This will be plus 6, plus 25. This is most certainly not going to equal -7, right? 32 plus 6 is going to be 38. 38 plus 25 is going to be 63. Yeah, 63. So now looking at this, we have 63 equals -7. Clearly that's not a true statement. I don't even have to go through the work of plugging it into this middle equation. So I found out when I plugged it into this first one here that it didn't work. That's enough for me to say, nope, this is not a solution. Oops. There we go. Not a solution. So we'll go over to part B, -5, 4, 5. We already talked about how it meets the requirements down here of z equals 5. So I'll start once again with 4x minus 3y plus 5z equals -7. So 4x minus 3y plus 5z equals -7. Instead of x, I have -5. Instead of y, I have 4. And then instead of z, I have 5. So we have -20 minus 12 plus 25 is equal to -7. -20 minus 12 is -32. -32 plus 25 is indeed -7. So we're not good yet, but we do know that it satisfies the first equation. Checking the next one, so that's the -5y plus 6z equals 10. -5y is 4, and z is 5. -20 plus 30 equals 10, and that's true. We get 10 equals 10. The very last one is just z equals 5, which we do know that. We know that 5 is equal to 5. So it works for all three equations, which means we can say that this is a solution to the system because it makes all three equations true when you plug it in. All right, so let's talk about the number of solutions a linear system can have. Now, in particular, I'm going to be talking about in 2 variables, but everything I'm about to say is also true in 3 variables, 4 variables, 5 variables, and so on. So the number of solutions it corresponds to the number of times that the 2 lines you have intersect. So there's 3 possibilities of what can happen. We could have 1 solution, we can have infinitely many solutions, or we could have no solution. Let's talk graphically what each one of these would mean. Our best case scenario is there's 1 unique solution. So this is going to happen when you have 2 lines, they intersect at 1 point, and exactly 1 point. These will never intersect again, right, because they're lines, and they just keep going off this way and this way. That solution is just that coordinate point, and there's only 1 of them. This is the solution, no other solutions. In order for this to happen, the slope of each line needs to be different. If the slopes are the same, you're going to end up with one of the 2 other things that can happen, which is either they're the same line or they're parallel lines. So they don't need to be perpendicular, so you don't need to worry about the opposite reciprocal thing, if that's kind of sitting somewhere in your head. That has to do with perpendicular lines. They don't have to be perpendicular. They could just need to have different slopes. That's all. In the case of infinitely many solutions, this is going to be where both lines have the same slope and y-intercept. And if both lines have the same slope and the same y-intercept, that means that both lines are the exact same line. So you have one line here, and then I kind of squiggled it in the other line there, but they're just sitting on top of each other. Technically, you have two lines, it's just that both lines are identical. So the lines lie on top of one another, which means they intersect at every point. They intersect here, 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 here. Every point is an intersection. The solution to this is technically a line. There's infinitely many solutions, and here's the whole line. All of those points on the line are solutions. So we typically write our answer, if we're writing it as a coordinate point, we write it as x, comma, mx plus b, because y is equal to mx plus b. That's just the equation of the line. Finally, we could have no solution. This is going to happen when we have parallel lines that have different y-intercepts. So they're parallel, they don't have the same y-intercept. If they had the same y-intercept, you'd have infinitely many solutions. But if they have different ones, they're just going to be parallel lines. They are never going to intersect because they are parallel. That's just by the definition of being parallel. So there's no solution to this system. So those are our different options for what can happen when we solve a system. Either there's one solution, infinitely many solutions, or no solution. You're never going to have a situation arise where there's two solutions only, or three solutions only. Either there's one, there's infinite, or there's none. So let's use that information and talk about how we can solve systems. We know now about how many solutions we're looking for, anywhere from none to infinitely many. And so let's talk about how we can actually solve these systems. So in general, there's three. Sorry, my Apple Pencil died there in the middle of a sentence. So in general, there's three different methods that we use to solve systems of equations. There's the method of graphing, which is where you graph both lines and you just see where they intersect. The next method is the method of substitution, where you solve for one variable in one of the equations, then you plug it into the other. And the last is the method of elimination, which is sometimes called the method of addition, where you multiply one or both equations by a constant, add the equations together to eliminate one variable. Now, I'm going to go in depth into each of these methods, but this is just a broad overview of the three different methods that we use to solve the equations. We're going to start by talking about graphing, then we'll talk about substitution, and finally we'll talk about elimination or addition, whatever you want to call it. So let's look at graphically solving a linear system. We have this system, y equals 1/2 x minus 2, and negative 2x plus y equals 1. Now, when you're asked to graph a system to find its solution, you have to actually graph the system. Even if you have a different method you wanted to use here, if you're doing Alex is going to have a grid for you where you actually do need to plot the lines and show where they intersect. So even though you might have a different method here, let's talk about the graphing method. We need both of these lines to be in y equals mx plus b form so that we can, utilize them the way we want to. The first line, this guy right here, is already in y equals mx plus b. His y-intercept is negative 2, and then his slope is 1/2. So rise over run, that's up 1 over 2, up 1 over 2, 1 over 2. Just I'm going to go in the backwards direction too to try to get the best line possible. Alex will do a good job for you because it'll do the line straight. All right, so this is our first line. Let's get the second line into its form that it needs to be in. So we want it to be y equals mx plus b, which means I need to add this 2x to both sides. And I get y equals 2x plus 1. So that y-intercept is going to be 1. And then it's up 2 over 1. Up 2 over 1, up 2 over 1, 2 over 1, and then I'm going to extend it backwards, and this is where it hits. So I'm going to ultra highlight that point. So right here, the point -2, -3, That's our solution. It's the place where those two lines intersect. So -2, -3. Now, we can always hope that that's the answer, but maybe a better option here is we can take this and plug it back in to both of these equations and make sure that we get true statements. We can check our answer that way. So let me just move this guy over here and we will check. So in the first equation, we have y equals 1/2 x minus 2. Y is -3. 1/2 x is -2 minus 2. So you have -3 equals 1/2 times -2 is going to be -1. So we have -3 is equal to -3, so it works in that first equation. In the bottom equation, let's try plugging in. So -2 times -2 is +4, minus 3 equals 1, and we get 1 equal, oops, accidentally hit the next page button twice. Let me just move it over here. 1 equals 1. And so it works in both equations, and we can feel good about that answer. So here was a situation where we ended up having just one solution. Let's look at another one. Here we have y equals -1/3 x minus 1, and then -x minus 3y equals 3. So I'll start with graphing this line because it's already in y equals mx plus b form. Its y-intercept is -1, and then negative slope means we're going to be going down and then to the right. So rise over run, down 1, right 3, down 1, right 3. And then extending that in the opposite direction. There we go. So there's our first line. Let's go ahead and put our second equation into y equals mx plus b form. -x minus 3y equals 3. We'll start by moving that x term over. So these cancel. We get -3y equals x plus 3. To get rid of the -3 in front of the y, we'll divide everything on both sides by -3. We get y equals, now x over -3, this is going to be the same thing as -1/3 x. So instead of writing x over -3, I will write -1/3 x. And then 3 over -3 is -1, so it'll be -1, which is interesting because this line right here, y equals -1/3 x minus 1, these are the same line, right? If I go to graph this, I'm just graphing the same line. If you run into this on Alex, you only need to plot the line once. You don't need to plot the line twice. So we know that there's infinitely many solutions here because they are the same line. They intersect everywhere. And the way that we could write our answer is as x comma, now let's go back to that slide real quick. It said x comma mx plus b. So whatever, since both lines are the same, it's whatever your mx plus b form is goes in place of where y would normally be. So here, -1/3 x minus 1, it's the same on both of them because they're the same line, would go right here for your y spot. You don't actually plug in values for x and y here, or in particular for x, because x is what you end up seeing here. So that's what it's going to look like if you are graphing and you end up with infinitely many solutions. Let's do one more graphing one. I'm sure you can kind of see where this is all going, but let's do one more. Start by graphing this first line. So it has a y-intercept of -1, and then its slope is -2, so that's down 2 over 1. And then I'm going to extend it in the upward direction. All right. And now I'll take my second line and put it into mx plus b form. I'll start by adding the 4x to both sides. I have negative 2y equals 4x plus 6. I want to divide everything by negative 2. So I get y equals negative 2x minus 3. So minus 3 is the y-intercept. And then it has a slope of negative 2, so that's down to over 1. And extending this backwards, these lines are very close together, so this will be something I have to be very delicate with when you're doing it by hand. Ooh, very, very close together. So this line is y equals negative 2x minus 3. Now, in general, if you're hand drawing something, you can't really say that two things are parallel unless you absolutely know they're parallel. So let's look at the line form. If you notice, both of these lines have the slope negative 2. So because they have the same slope, they are parallel lines. They have the same slope, but different y-intercepts, which makes them parallel lines, meaning that they never intersect. So we're going to have no solution on this one because they do not intersect anywhere. So that's that for the graphing method of solving systems. Let's go look at our remaining two methods. Let's talk about the method of substitution and kind of go through what this process looks like. So the method of substitution is going to involve solving for a variable, either x or y, in one of the equations and plugging it into the other. So the first thing you need to do in order to do that process is to solve for one of the variables in one of the equations. Note, as a tip, it's easiest to solve for variables who have a coefficient of 1. So in particular, if I'm looking at either of these equations, in both equations, y has a secret coefficient of 1, so y would be a good one to solve for. And it doesn't matter if you choose the first one or the second one. I'm going to go ahead and choose the first one, just because it's right there. Let's go ahead and use a different color. Let's use purple. So we have negative x plus y is equal to 3. We want to solve for y, so get y by itself. We're going to add x to both sides. Then we have y equals x plus 3. So this equation here is the same thing as y equals x plus 3. So since we're kind of running out of some room here, I'm going to go ahead and move this right here to the next slide to talk about our next point. So here we have that system, same system. So our second step is substituting the expression found in step 1, which is this guy right here, draw an arrow, into the other equation. So we solved for y in this guy, we need to plug y equals x plus 3 in for y down here. Really important here that you do not substitute it back into the same equation you used in step 1. So if you try to put this guy back into here, you're going to end up with some problems. You'll get a true statement. You just don't want to do it. You're going to run into issues. So you're plugging it into this guy down here. So I have 3x plus y equals negative 1. Now instead of y, I'm putting in x plus 3. So 3x plus x plus 3 is equal to negative 1. So we've substituted it into the other equation, hence the method of substitution name. All right, so then our next step is going to be solving this equation. We have 3x plus x plus 3 equals negative 1. Combining like terms, we get 4x plus 3 equals negative 1. Subtracting that 3 on both sides. We get 4x equals negative 4. and then dividing both sides by 4 to cancel this 4 out, we get x equal to -1. So we know we're looking for an answer that looks like this, x comma y. We have now found the x portion. We just need to find the y portion. So let me kind of move things around a little bit and kind of have this portion right here and this portion here, making room for the next step here. So we have x equals -1. Our next step is plugging the solution back into your step 1 equation to solve for the other variable. Technically, you could plug into either of these. You could take your -1 and plug it in here or here, and you'll get an answer for y, but it's easier if you're doing substitution. Since you've already solved for y, it's much easier to plug it back into this original equation we worked with. So y is equal to x plus 3. We know that x is -1, so y is equal to -1 plus 3. So y is equal to 2. So we have an answer right now. We want it as an xy, so a point x comma y. Here we have -1 comma 2. We're going to claim that that's our answer. But we are good students, and one thing in math we can do is check our work, right? We talked about how to check whether or not something is a solution, so we should do that. This was the previous step, we found our point. Let's check the solution by plugging x and y into both original equations. So it's really important that you go back to before you did anything here, because there's a possibility that between here and here, something went wrong and that you got this guy wrong. So you really want to go back to this very original one to double check and make sure that everything is okay. So if we start with -x plus y equals 3, our x is -1, so -1 plus y is 2 is equal to 3. -1 is just +1 plus 2 equal to 3. Yep, that works. Let's try the next one. 3x plus y equals -1. So 3 times -1 plus 2 is equal to -1. -3 plus 2 is equal to -1. Yep, that works too. So we can feel good about our answer, and this guy right here is our answer. So once again, quick review. First, you're solving for one of the variables in one of the equations. Then you're going and you're substituting whatever you solved for here into the other equation. Then you solve after the substitution, you'll get an equation where you'll only have x's or y's left. You'll only have one of them. If you have an x and a y left at this point, something has gone wrong. Okay? You'll be able to solve for one of the variables at this point. You solve for that variable, then you plug the solution back into what you solved for in step 1 to get your other variable. So we were able to get y equals 2. And then you want to be able to check your solution. So make sure that you go ahead and check your solution. Let's go ahead and do another one, but we won't write down the steps each time. We'll just go straight through it. So 3y minus 6 is equal to x. -3x plus 2y is equal to 11. When I look at this, I notice right away that x has already been solved for in this first equation. X is on the left here, but we could easily write x on the left and have this be 3y minus 6. So we already have x solved for. We're good to go to the next step, which is plugging this in down here. So I have -3, and instead of x, I'm going to put in 3y minus 6. You need to use parentheses here. Plus 2y is equal to 11. Notice that we only have y's left at this point, which means that we are going to be able to solve for y. Distributing the -3, we get -9y plus 18 plus 2y is equal to 11. Combining like terms, we have -7y plus 18 is equal to 11. Subtracting 18 on both sides. -7y is equal to -7. and then dividing both sides by -7, we get y is equal to 1. Y is equal to 1. So our answer is going to look like this. We just need to figure out what goes right here. We're going to take this 1 and plug it back in to the equation we solved for originally, and that'll give us our x. So x is equal to 3 times y is 1 minus 6. 3 minus 6, x is equal to -3. So let me write that a little nicer. Our answer is -3, 1. We're good students, so we're going to check it. Looking at the first equation, 3y minus 6 equals x. Right? X, y, remember. So y is 1, so 3 times 1 minus 6 is equal to x is -3. 3 minus 6 equals -3. Yep, that looks good. Let's look in the second equation. -3x plus 2y equals 11. X is -3. Y is 1. -3 times -3 is +9. Plus 2 is equal to 11. This is looking good. So when we plugged it back in, we got true statements both times. So we can say -3, 1 is the answer to this system. So that's the method of substitution. There's one method we have left to talk about, and that's going to be the method of elimination/addition. This is going to be, I would say, the most complicated of the versions, but once you get a hang of it, it's going to be fine. It really just takes practice, and it is worth practicing these skills because these skills come in handy in basically every other math class you take. So definitely take the time now to learn these skills. Let's go look at the method of elimination, or the addition method, as Alex calls it. At least I believe they call it the addition method. I can actually check right now. Oh no, they do call it elimination. All right, so the elimination method, but some people call it the addition method. All right, so here we go. I'm going to point off right off the bat why this isn't a great contestant or contender for the method of substitution. It's not easy to solve for x or y in any of these. If I tried to divide by 5 here to get x by itself, I'd have fractions, and I really don't want to deal with fractions unless I absolutely have to. So neither of these equations are going to give me a nice like x equals or y equals. So substitution isn't going to be best here. So what we'll start by doing is writing each equation in the ax plus by equals c form. The bottom equation is fine. That's already done. It's just this guy up here that we need to mess around with. So 5x equals 4y plus 6. We want to get the y on the other side, so we will subtract 4y on both sides. And we get 5x minus 4y is equal to 6. So our new system is 5x minus 4y equals 6, and -3x plus 7y equals 1. So all I really did here was substitute this new form of this equation in for it. So I took this guy and just rewrote it in a different form. So let's look at the next step. Right, so I didn't rewrite our system fully, but we do have the one thing we needed from the previous step. Our next step is multiplying one or both equations by constants such that if you were add straight down, one variable would cancel out. So if I just kind of look at this as it stands, you're allowed to add two equations to each other. Since both things on both sides are equal, if you add these sides together and add these sides together, you should get two things that are equal still. So one of the things we can do, we can add two equations together. And of course, this guy's missing an x. And if I do that, I get 5x minus 3x is 2x, -4y plus 7y is plus 3y equals 7. Now, this didn't bring me any closer to the truth to an answer at all, right? Sad face. I'm no closer to an answer when I do this. However, we can abuse this and make it such that when we add straight down, something cancels. And it's up to us to decide what's going to cancel. There's multiple, in fact, infinitely many correct answers here. That doesn't mean that everything you do is correct, but there are infinitely many correct ways to do it. So you're going to multiply one or both equations by constants such that if you were to add straight down, one variable would cancel out. So I'm going to rewrite this guy. 5x, let's use black pen. 5x minus, I don't like the way that 5 looks. 5x minus 4y is equal to 6. 2x plus 3y is equal to 7. And we're not using this at all. This was just illustrative purposes, that nothing good happened when we just added them straight together. So coming down here, now we are either going to cancel the x's or we're going to cancel the y's. And what did I do here? I accidentally wrote the wrong equation there. I should have been writing this equation down. I did not do that. So negative 3x plus 7y equals 1. Okay. That's the equation we're working with. So we're either canceling x's or we're canceling y's. Notice that they're both opposite signs. That would be one of the ways I would determine which is a better one. They need to be opposite signs so that when you add straight down that they cancel. So x and y don't have, neither x nor y has an advantage over the other at this point. Then the next thing to look at would be, are there any multiples we can take advantage of? For instance, if we had 5x, let's say if we had 6x and negative 3x, well, then all we would have to do to this guy would be multiply by 2, and then you would have 6x and negative 6x. So we're looking for any multiples we can take advantage of. But we don't have any, so negative 3 doesn't multiply to 5, same thing with 4 and 7. So we're going to end up multiplying both equations by some number, your choice at this point. I'm going to go ahead and cancel my y's first so that I'm solving for x. I need these to multiply to the same, I need these to become the same number, which means I need to multiply both equations on both sides by numbers such that these will cancel. The first number that these guys both multiply to is going to be 24. Not 24, 28, 28. Those moments, right? So if I multiply by 7 here, and I really should be more careful about this and do 7, and then I want this 7 to turn into a 28. So I'm multiplying by 4 to make that happen. Remember that you are distributing when you do this. So 7 times 5 is 35x minus 28y is equal to 42. And then we have negative 12x plus 28y is equal to 4. When we add straight down, 35 minus 12 will be 23x. The y's cancel completely, and this is equal to 46. So we have the equation 23x equals 46. Now I did get a bit ahead of myself there because step 3 was actually supposed to be adding the equations together. So technically this step is just the multiplying step. Your next step is where you add them, and then you're able to solve for the remaining variable. So I can now solve for x by dividing by 23 on both sides, and those will cancel. I get x is equal to 2. Now all we have left is to figure out what y is. And remember that x is 2. Let's go to the next slide. And then just write up here x is equal to 2 to remind us. Step 4 is substituting the value you got in step 3 into one of the original 2 equations and solving for the other variable. So in either of these equations, we can put in 2 for x and then solve for y. It doesn't matter which. In fact, I'll show you that you can do either. So if I look at the first equation, 5x equals 4y plus 6, and I plug in 2 for x. Here we get 10 is equal to 4y plus 6. Subtracting 6 on both sides. 4 is equal to 4y. Divide by 4 on both sides. These 4's cancel. And we get 1 equals y. So our answer is going to end up being 2, 1. But let's say that we didn't use this equation. Let's say we had instead used the bottom equation, negative 3x plus 7y equals 1. Would we have got the same answer for y? Well, plugging in just the 2 and we'll solve for y. So negative 3 times 2 plus 7y equals 1. This will be negative 6 plus 7y equals 1. Add 6 to both sides. 7y is equal to 7. And voila, you get y equals 1. So either way, either equation, as long as you've done everything else right, you'll get the same answer when you go to find the last variable. Our final step on these, checking our answer. So we're going to plug our answer into both of these equations, the originals, and make sure that everything comes out okay. So 5x equals 4y plus 6. 5 times 2 is equal to 4 times 1 plus 6. 10 is equal to 4 plus 6. That looks good. So we're good in the first equation. Let's check the second one. Plugging in 2 for x, 1 for y. Negative 6 plus 7 is equal to 1. Looks good to me. So we can feel confident about our answer because we've checked it. 2, 1 is the answer for this problem. So let's try that again without writing the step-by-step process down. Here we have 7x plus 6y equals negative 4, and 4x plus 6y equals 8. Now, let me just kind of rewrite these guys where I have more room. When I look at this, substitution doesn't look like a good method to me because I don't have 1s as coefficients on any of my x's or y's, so that doesn't sound like a good option. So I'm looking at elimination. I want to have something cancel when I add straight down. Now, if I added straight down right now, these guys wouldn't cancel, they would turn into a 12y. However, if I could make one of these 6y's into a negative 6y, then they would cancel. So I'm going to do just that. I'm going to multiply one of them, and it doesn't matter which, by negative 1 on both sides. Make sure you are distributing. So we'll get negative 7x minus 6y is equal to positive 4, and then we are leaving the bottom equation alone. Do you see how these 6y's can now cancel because they are opposite signs? So negative 7x plus 4x gives me negative 3x. The y's cancel. 4 plus 8 is equal to 12. Divide both sides by negative 3. We get x equal to negative 4. We're going to take this negative 4 and plug it into one of these two. Doesn't matter which. I guess I'll take the first one. So 7x plus 6y is equal to negative 4. We are now solving for y. So I'm taking the value I know, which is negative 4 is what x is. and plugging it in. So we have negative 28 plus 6y is equal to negative 4. Adding 28 to both sides, we get 6y is equal to 24. Divide both sides by 6. Y equals 4. So our answer is negative 4 comma 4. But we are good students. We are going to check our answers. So 7x plus 6y equals negative 4. 7 times negative 4 plus 6 times 4 equals negative 4. So negative 28 plus 24 equals negative 4. Yep, that checks out. Second equation, 4x plus 6y equals 8. 4 times negative 4, 6 times 4 is equal to 8. Negative 16 plus 24 is equal to 8. And that all checks out. So because we got true statements on both of the equations when we plugged x and y back in, we can say negative 4 comma 4 is the answer to this system. So let's do another example with elimination. We have negative 4x minus 7y is equal to 9, and negative 2x minus 9y is equal to negative 1. Once again, I'm going to write them down here so I have more room to mess around with them. When I'm looking at this, I'm thinking of how I can get things to cancel when I add straight down. And I notice that 2 and 4, right? 4 is a multiple of 2. So if we multiplied this equation by 2, we'd get a negative 4 here. If I wanted them to cancel, I could multiply this entire equation by negative 2, and this would become a positive 4. You could do the y's here, but just kind of thinking about what would make your life easier, if I tried to cancel the y's, I would have to multiply both equations by some number. However, to get the x's to cancel, I would only need to multiply one equation by a number. So I'm going to multiply this equation down here by negative 2 on both sides. Distributing the negative 2. So the first equation is negative 4x minus 7y equals 9. The next one is positive 4x plus 18y is equal to positive 2. Notice that when we add straight down, these x's cancel. Negative 7 plus 18 is 11y equal to 11. Divide both sides by 11, we get y equals 1. So we know y is equal to 1. You can plug back into either equation here, doesn't matter which. I think I've used the first equation like the last 2 times. I'll just use this one now. So negative 2x minus 9y is equal to negative 1. We know that y is 1, so we will plug that in. So negative 2x minus 9 is equal to negative 1. Adding 9 to both sides. Negative 2x, don't like that negative sign, negative 2x is equal to positive 8. Dividing both sides by negative 2. We'll get x is equal to negative 4. So the point negative 4 comma 1. Now, we should check it. I'm going to go ahead and pause it and run through the math so you don't have to see me running through it, but that you can verify afterwards. So pause for a second. All right, so I checked it. First equation, 9 equals 9. Second equation, negative 1 equals negative 1. So negative 4 comma 1 is our answer. So let's make it a little harder. Let's introduce some fractions into the mix. All right, we have 2 equations and both of them involve fractions. Most people do not like fractions, so the best thing we can do here is get rid of the fractions by multiplying each individual equation by its LCD, its least common denominator. So looking at the first equation, the least common denominator, looking at 5 and 5, those are the only denominators. Don't worry about him. He doesn't have a denominator to worry about. The smallest number that 5 multiplies into is itself, which is 5. So the LCD on this guy is 5. So we will multiply this equation by 5 on both sides. So we have 5, and then 1/5 x minus 2y equals, and then 5 on the other side. Distributing the 5. The 5s are going to cancel on the first guy, so you'll just be left with a 1x, which I will write as x. 5 times -2 is -10. And then on the right-hand side, those 5s cancel, and you get -2. So this is the same as x minus 10y equal to -2. Looking at the bottom equation, this time we're looking at 3 and 2. The LCD of 3 and 2 is going to be 6. That's the first number that they can both multiply to. So I'm going to take 6 and multiply by that on both sides. Now, you could, of course, deal with the fractions if you wanted to. You don't have to do this. You don't have to clear out the fractions. It just makes your life a little bit easier. Distributing 6. 6 times 1/3, that's the same as 6 times 1 is 6, divided by 3 is 2. So this will be 2x. 6 times 1/2, same as 6 divided by 2, that's 3. So 2x plus 3y equals 42. So what I could do at this moment is pretend that my system said x minus 10y equals -2 and 2x plus 3y equals 42. I have options here. I could do the method of elimination. I would choose to multiply this guy by -2 if I were to do that, because then this would be a -2x and a positive 2x, and they'd cancel. But we also have the option here to do substitution really nicely, because this guy is just a regular old x with a coefficient of 1. So if I go to do substitution, looking at that first equation, x minus 10y equal to -2, I can get x by itself by adding 10y on both sides. So we get x is equal to -2 plus 10y. Now I'm going to take this and plug it in for x in this bottom equation. So this guy right here. So I have 2 times, instead of x, right? Instead of x, ooh, let's do purple. I'm going to be putting -2y plus 10. So -2 plus, did I say -2 plus 10y? If I didn't, I meant to say -2 plus 10y, because that's what x is equal to. Once again, we're looking at this equation right here. So I have the 2x part. Now I just need plus 3y equals 42. Distributing, -4 plus 20y plus 3y is equal to 42. Combining like terms, we get 23y minus 4 is equal to 42. Adding 4 on both sides. 23y is equal to 46. Ooh. Sorry, things froze for a second there. So 23y equals 46. Dividing by 23, we get y equals 2. So coming and setting up my answer over here. Now I can easily solve for x by plugging 2 into this formula. So x is equal to negative 2 plus 10 times 2. X is equal to negative 2 plus 20. X is equal to 18. And we get the answer 18, 2. Now for checking this one, you probably want to plug it into a calculator because it's going to involve fractions. So I would take each of these and I would use your calculator to plug it in. I've just done that myself, and indeed everything works itself out, so we can feel good about our answer. Let's do one more fraction problem, and then we'll start talking about 3 variables. We won't have a long conversation, don't worry, you're almost at the end. So negative 1/3 x plus 1/6 y is equal to 8, and then 3/4 x plus 1/2 y is equal to negative 11. I want to multiply by some LCDs here. For the first equation, the LCD is going to be 6. So I am probably just going to make this a mess. Ooh, no, let's not do that. The LCD is 6. So I will take and multiply by 6 on both sides. Six divided by 3 is 2. 2 times negative 1 is negative 2. So this will be, when I distribute it, negative 2x, and then 6 times 1/6, and you can just do 6 times 1/6 in your calculator, that's fine too. That's going to be 1, so I'm just going to put plus y, and then 6 times 8 is 48. For this equation down here, our LCD is going to be 4. So I'm multiplying by 4 on both sides. So 3/4 x plus 1/2 y, and then 4 and negative 11. Just like we did with the 6, we are going to distribute. When you distribute it to the 3/4, the 4's just cancel and you just get 3x. And then 4 times 1/2 will be 2, so plus 2y is equal to negative 44. So our new system is negative 2x plus y equals 48. And 3x plus 2y equals negative 44. Things aren't quite right yet because if we added straight down, nothing would cancel. We did substitution on the last one, and we could easily do substitution again if we wanted because we could solve for y here. But let's go ahead and do another elimination one. I notice I can pretty easily make the y's cancel. All this needs to be is a negative 2. So I'm going to take the first equation and multiply it by negative 2 on both sides. So negative 2 times negative 2 is 4x, and then minus 2y is equal to negative 96. And then the bottom equation will stay the same. So 4x plus 3x is 7x. The y's cancel. Let's see, this is going to be negative 140. Dividing by 7 on both sides. I'll get x equal to negative 20. So we just need to solve for y. Now, you could take one of these guys and plug your x back in. However, it might be better to take one of these guys over here. Even though there's a small chance that you went wrong from here to here, I would still take that chance and use one of the fractionless equations to solve for y. I notice this guy doesn't have a coefficient on y, so I'm going to choose this first equation here to solve for him. So negative 2x plus y equals 48. Negative 2 times x is negative 20 plus y equals 48. So 40 plus y equals 48. Subtracting 40 on both sides. Y is equal to 8. And we have the answer, negative 20,8. Now, once again, calculator is probably best for checking your answer. I would not check your answer using these guys. I would check your answer using this original one and your calculator. So I'm gonna pause, do that real quick. All right, done in the blink of an eye, and it does come out right. So negative 20,8 is our answer here. So this kind of leaves us with one last thing to talk about, and it's something that was brought up at the very beginning. I talked about these systems where you have 3 different variables. We're not going to go too hard into this. We're just going to kind of go lightly into it. There are more difficult systems that will require some algebra that you'll learn if you go to take linear algebra, which is a higher up math course. You'll learn more about those methods, but we're going to deal with some simple cases of these, we call them 3x3 systems. 3 equations, 3 variables. And these are the ones that you'll be running into on ALEKS. So here we go. We have this system right here, negative 3x plus 6y plus 4z equals 8, 5y minus 2z equals negative 9, and negative 5z minus 10, or negative 5z is equal to negative 10. It's easy. If you have it so you can easily solve for one variable, all you'll need to do is solve for the variable, and then we can just kind of keep on plugging in. So we can solve for z here. If we plug z in, we can solve for y. Then we have y and z. We can plug them in and solve for x. So that's the process we're going to take. We're going to start with this guy here. Negative 5z is equal to negative 10. Dividing both sides by negative 5. We're going to get z is equal to 2. Then we're going to look at this equation. 5y minus 2z is equal to negative 9. We know that z is equal to 2, so we will plug that in. 5y minus 2 times z is 2 equals negative 9. 5y minus 4 is equal to negative 9. Adding the 4 on both sides. 5y is equal to negative 5. Divide by 5. Y is equal to negative 1. So now we have y and z. We can come to this equation, which is actually the first equation, but we're doing it third. And that's going to be negative 3x plus 6y plus 4z equals 8. We know what y is, right? Y is negative 1. Plus 4 times z is positive 2 equals 8. So negative 3x minus 6 plus 8 equals 8. Negative 3x plus 2 equals 8. Subtract 2 on both sides. We're trying to solve for x. Negative 3x is equal to 6. Divide both sides by negative 3 to get x by itself, and we get x is equal to negative 2. So altogether, so the way that our answer should look is x, y, and then z. So x is negative 2, y is negative 1, and z is 2. And that's our final answer. We should plug in our answer to make sure that it comes out okay. You would need to plug it into all 3 equations. So maybe what I'll do is kind of scrunch this together, write it down, pause the video. So I'm going to pause the video, write the checking down, unpause it. Hold on. And there it is. So everything came out totally fine. If you want to check it yourself, you can go through my math here, but everything works when I plugged x, y, and z in for all three of these equations. So -2, -1, and 2 are our answers. Let's do one more of these, and that's it. That's all I have for you, just one more of these systems where we have three variables to solve for, and we'll be done. So here it is. -2z equals -6, 4y minus 3z equals 3, and -6x plus 6y plus 5z is equal to 3. It looks like it would be a good idea to start right here with this equation, -2z equals -6, because we can solve directly for z. So -2z equals -6, dividing by -2 on both sides, we'll get z is equal to 3. Now we'll look at the equation that has two variables in it. We know z is 3, so we can plug that in. So I'll write down the full thing first. So 4y minus 3z is equal to 3. 4y minus 3 times z is 3 is equal to 3. 4y minus 9 is equal to 3. Adding 9 on both sides. 4y is equal to 12. And we get y equal to 3. So now we're going to work with this last equation. -6x plus 6y plus 5z is equal to 3. We know y is 3. We know z is 3. So we'll leave x alone because we don't know what that is yet. Like we said, y is 3. Z is 3 as well. Equals 3. -6x plus 18 plus 15. We're just combining like terms at this point, simplifying. So plus 33 equals 3. Subtracting 30 on both sides. Oh, not 30. 33 on both sides. So -6x is equal to -30. Divide both sides by -6. X is equal to 5. So our final answer, 5, 3, 3. And there you go. Once again, I'm going to pause it, show the checking of the work, and then you can verify that. So there you go. There's the checked work. It all comes out beautifully. 5, 3, 3 is our answer. So that's all there is for this video. We don't go too hard into those 3x3 systems. You'll run into them later in your math career and you'll deal with them a little bit more in detail then. But for now, really, the ones that I'm having you do are, I would say, more simple than the 2x2 systems because you'll be outwardly able to solve for one variable to begin with. All right, so just keep practicing these, keep practicing, and this is actually the last video for this class, so I would say see you in another video, but this is it. So I hope that you have enjoyed this video series on math. If you're not my student and you're just some stranger watching this, I hope you enjoyed this half a series of Math 127, which is our trigonometry class. If you are my student, and especially if you're my student right now during the COVID-19 pandemic, I don't know how long I'm leaving these videos up, but it could be for a while. I'm sorry that our semester got torn in half. I really wish we'd had the opportunity to finish it together in person. Hopefully these videos have been helpful though, and hopefully I see you in the future sometime. You know, obviously not in this class, but hopefully I see you around. All right, bye everyone.